Hi, good morning, good evening, or good afternoon, depending on when you are seeing this and where you are. Um, I came across an interesting trolley problem, which is a meme. And it's one of those memes where the joke of the meme is that the meme, instead of being a meme, is a very complicated math problem. And I laughed and I thought it was very funny. And then I wondered if I could solve it. And I have been solving it for the past 2 hours. And the problem deals with quantum mechanics and philosophy, both of which I know very little about. So I had to spend some time reading up on quantum theory and a little bit of philosophy. And I've been a very bad sort of like math and science student. Anyway, yeah, I've been a like really poor math and science student since school. Like I was so bad that I had to take commerce in 11th grade, and even when I took commerce with math, I was consistently bad in math. I had really low grades throughout my high school in math, at least. So um so it was really interesting to me for me to solve this. At the end of the day, it wasn't hard in a, you'll see. But what I really want to emphasize is how you can learn a lot if you want to over the internet, and then you can do random things with it, like I did by solving a meme. So I'll explain my solution now. And yeah, it's a pretty interesting meme slash problem, and maybe we'll have some fun with it. So we're looking at two gates, two slits from which the trolleys can sort of enter. There's slit 1 and slit 2. Each of the gates is followed by a crystal which divides the energy of the waveform of the train into two. So every time 50% of the train is divided into this part, which has one person, and the other 50 goes to this, which has multiple possibilities. If you pull the lever, you will be able to detect which gate the train passed through. And if you don't pull the lever, you won't be able to detect which gate the train passed through. And that is where some interesting quantum mechanics comes into play. So if you were to pull the lever and find out which gate the train passed through, the solution is fairly simple. What you do is you'd find out the average number of people killed if you pull the lever. So there's a few different cases, right? In the first case, if it passes through gate 2, it kills one person, but then it also kills 4 people. So that's 5 people, and then 1 and 0, so that's one person. Oops. And then 1 and 1, so that's 2, and so on. So 5 plus 1 plus 2 plus 2, this is five different possibilities by 5. And if it passes through gate 2, then it kills one person, and then one person, one person, one person. So 2 2 2 by 3, and we do the average. We'll find out that on an average, if you pull the lever, 2.7 people will be killed, which is the average of every probability. Sometimes it will be more, sometimes it will be like how many, 5 people can be killed, and sometimes maybe only one. At least one person will die all the time, but on an average across every possibility, 2.7 people will die. Now we'll look at some of the quantum mechanics stuff. So the other case is, if you do not pull the lever, what can happen? And the problem mentions three possible theories of quantum mechanics. Hi, so the problem mentions three possible theories of quantum mechanics, and we'll look at each of those theories and we'll try to figure out the average number of people who die in each of the scenarios in which that particular theory is true. The problem also mentions you don't know whether theory A, theory B, theory C is true, or any other theory, but we'll skip the or any other theory part because that makes the problem too complicated. We'll assume either theory A or theory B or theory C is correct, and will assign a probability of 1 by 3 to each of them, which means that each of them is equally likely to be correct. And we'll try to find out how many people die on an average if each of those theories are correct, and we do not pull the lever and we do not find out which gate the train passed through. So if we assume the many worlds theory is correct, then the problem itself mentions the solution, which is that in many worlds, many will die. In some worlds, some will die. In many worlds, nobody will die. And what the many worlds theory essentially assumes is that apart from every item being entangled with each other, you as the observer is also entangled with the particles of your universe. So every situation that could happen. So if you take the Schrodinger's cat's problem, the Schrodinger's cat is alive and dead in different worlds. But in the world where the Schrodinger's cat is alive, you get to see the Schrodinger's cat as alive, and in the one where it's dead, you get to see it as dead, and you are entangled with the cat as being a dead cat, and you are entangled with the cat as being an alive cat. And these are separate worlds where the particles are entangled in different ways, and there is no overlap, so there is no possibility of communication. So what this means is that in every universe where a specific probability could exist, that probability does exist, and the probability of that event happening is 1. That event will definitely happen in that particular universe, whereas in a different world, something different will happen, and the probability of that happening in that world is 1. That event will always happen in that world because you as the observer is entangled with that event in that world. And because there is no overlap between the entanglement of these particles, there is no way of verifying whether in another world something different has happened. So many world theory means many worlds where many different things will happen. You are entangled with the event. In every event that happens, the probability of that event happening in that world is 100%. Apologies for the bad handwriting. So each of these different cases will happen in different worlds, but you don't know in which world you will live in. So we'll assign each of these probabilities as 1. So there's a 5 into 1, and 1 into 1, and 2 into 1, and 2 into 1, and so on. And we'll divide that, and we'll essentially get 2.7 back. Because if you are in a particular world where a particular event happens, that event will definitely happen in that world, but you don't know in which world you are, so each event is equally likely. So 2.7. I hope that makes sense, or maybe I'm wrong. And then Copenhagen, that's the standard Schrodinger's cat's problem. Until you observe something, both events can happen. After you observe, the wave function, which is the probability function of both events happening, collapses, and then only one event can happen. Both events happening, which is a superposition, can only exist when you're not observing the thing. When you start observing the thing, the wave function collapses, and only one event can happen. So while the restriction is in, if you pull the lever, you will be able to observe which gate the train goes through. Even if you don't pull the lever, you will be able to eventually observe each of the cascades because you'll have to open them. I know the problem says something along the lines of you will not know how many people have died until you open the box through which the train passes, because that box is only transparent to the frequency of the train passing through. But eventually, to verify the solution, you will have to open each box, which is how I see this problem. So when you open each box, you will be able to destroy the wave function, and only one of the probabilities will exist, where, you know, of the 4, either 4 will die, or 4 will remain alive, or 3 will die and 1 will remain alive, and 2 will die and 2 will remain alive. But each of them will have an equal probability because there's an infinite likelihood of each of them happening. So because there are infinite events in which each of these happens, essentially it at the end boils down to normal average, and the normal average is, as we calculated, 2.7. So when you open these cascades, they are either alive or dead, but not both. And because they're either alive or dead, not both, the probability is 2.7. Oh, sorry, the average people dying in the event that Copenhagen theory is true and you did not pull the lever, 2.7 people will die. Okay, now the pilot wave theory. The pilot wave theory that assumes that both wave and particle states of a matter exist differently. Like, so in a departure from what is essentially assumed in quantum mechanics, where both particles and waves of energy or matter are the same thing simultaneously. Here they are different things in a way that the particles are guided by the waves, and they are actually different things. So these are the waves, and then the particles are like this, and when the wave moves, the particles also move, and the wave pushes the particle, and this, which is why the wave is the pilot, hence the name pilot wave. So in a double slit experiment, if you have a pilot wave, if you believe in the pilot wave theory, you will be able to predict where each of the particle lands, because you will measure it with the way that the wave is going, and that way you will be able to predict where each particle will land. That is essentially what the pilot wave theory is, according to what I understand. So all that is different here is that instead of almost instead of the normal problems that come with some other theories, we'll be able to predict where each state of the train will land. So this is the train. We'll be able to predict if it goes through a gate where it will land. But because the train is already traveling through tracks, and there is only so many possibilities that it can go to, we'll assume that again the probability is the same because the train is traveling on tracks. The train is not exactly free to move. And so the train will either go to any of these possibilities with the same probability as we had before, and hence the probability would be, oops, 2.7. I wrote it wrong here, it's 2.7. Okay, so 2.7. So in case you pull the lever, on an average 2.7 people will die. In case you do not pull the lever, in each theory, if we assume either of these theories are correct, in each theory 2.7 people die, and we'll divide by 3 because we don't know which theory is correct. So in case you pull the lever or you do not pull the lever, in both cases 2.7 people die. And let's go to the last section of the problem, which is philosophy. So you do not understand how this works, and you are a moral ethicist, I believe, a moral ethicist. And from what I understand, the principles of moral ethicism say that goodness must precede the rightness, and that right and wrong are according to the person. So in order to determine whether an action is right or wrong, you have to take into account the person who is performing the action and his entire life. You cannot just determine whether an action is good or not in a particular context. You have to assume the person performing the action, and you also have to take into account the person's entire life. And to take that into account, you have to ask these questions: who am I? Who ought I to become, and how ought I to get there? So in the question, you really do not understand, you, the person who is performing the action, do not understand how this works. And you haven't really caught up to the 20th century, and this is a complicated problem. You need to catch up to the 20th century to understand this. So the person, right and wrong according to the person here is pretty stupid, right? The action performed by the person is stupid. And because according to you, you do not understand this problem, and as a moral ethicist, right and wrong should be according to the person, and the person doesn't understand the problem, so he doesn't understand whether to pull the lever or not. You will not pull the lever, you will walk away from the problem because your philosophy training tells you to. I had a lot of fun chasing this rabbit hole down. It sort of puts you into perspective how it's probably pretty stupid, but you can chase down interesting rabbit holes and learn stuff. And this was hopefully a good use of about 2 hours of my time. Thank you for listening. Yeah, I'll see you later.